Nice. Yeah, it's great. Welcome, everyone. Thanks for coming. It's a great pleasure today to have Professor Gregor Weihs visiting us all the way from Innsbruck University and to present perspectives on quantum science in Austria and his work. Gregor is a professor for photonics at the Institute for Experimental Physics at Innsbruck University. He's also the director of the research cluster of excellence called Quantum Science Austria, and I think we'll hear something about that today. And furthermore, he's also the vice rector for research at the University of Innsbruck. So quite an official role to take. So that's great. Gregor himself did his undergrad studies and master's degree at Innsbruck University, and if I may say so, I was actually studying parallel to Gregor, or maybe just 1 year behind, so we knew each other for quite a long time. And so after Innsbruck, he moved to Vienna with the group of Anton Zeilinger for his PhD, and which he actually received with award, the Subauspecies Präsidentis, by the president of the Austria. So that was in the year 2000. So very impressive. And after that, he spent time in various places. He was an assistant professor at Stanford University, a research fellow at the University of Tokyo, and also for several years an associate professor at the University of Waterloo at the IQC in Ontario. And since 2008, I think, back in Innsbruck as a professor for physics. So very exciting, a very exciting path. Gregor's research interests are all the way from fundamental physics, experimental and theoretical quantum and semiconductor optics and quantum information. And in particular, he's focused on sources of entangled photons from nonlinear optics, but also quantum dots. And he's also studying the strong coupling of semiconductor devices, microcavities, with optics. So a broad spectrum of very interesting work. And so Gregor, thank you very much for finding time in your busy schedule to come here to visit us, and we look forward to hearing about the research activities. Thank you.
Thank you very much. Thank you so much, Thomas and colleagues, for inviting us here. It's not just me today. We have a whole delegation from Innsbruck and Vienna, and I have a really tough job. It's the first time I give a talk in front of my boss. I think maybe not. Considering that this is a special visit, I decided to say a bit first about our cluster of excellence, which is a format that's still the first round of this kind of network grant that was funded in Austria, and then therefore cut a little down on the actual physics presentation later. So we entitled this Quantum Science Austria, actually a name suggested by Peter Zoller, who many of you might know. And in setting this up, we went from the thought experiment of Schrödinger's cat, where one can study phenomena, or one can identify phenomena as quantum superposition, entanglement, and also the question of macroscopicity. And going from that, we thought, what are our strengths in Austria? And there's many things that have been invented. In fact, quantum mechanics has been invented in Austria by at least half of it. Yeah, or one formulation. And then what can we still do? And our strength has always been in fundamental things. And so we figured that we would take this and come up with three areas and study the influence or use or application of entanglement in three areas. This is gravity, or we call it the nature of space-time and gravity, in information and in matter. And at some point we went through the things that were invented in Austria in quantum physics, and if you look at this list, it's really massive. Quantum repeaters, Hans Briegel, Innsbruck, in the late 1990s. And even newer things like quantum machine learning, trapped ion quantum computing, of course, and all this is going on very strongly still. And so we teamed up, and this is 6 institutions across Austria. So this is a schematic map of Austria, and we have 2 institutions in Innsbruck, or we have the Academy of Sciences actually split between Innsbruck and Vienna. It's 2 institutes of the same. Then in Linz, somewhere in the center in Upper Austria, and then 4 institutions in Vienna. And I'm not going to say too much about this, but if we start in Innsbruck, there's a lot of nice things to read, but let me just pick out one thing that you might have heard about, and that is a demonstration of a full quantum repeater node based on trapped ions by Ben Lanyon and Tracy Northup. That is to say, the entanglement rate per time is not great, but it works very faithfully with very high fidelity. And they are scaling this up actually in a European quantum communication infrastructure. I'm very excited about this. Going further on to Linz, I want to highlight one thing, and this is called the sound of entanglement. They actually made a performance, so this is more towards outreach, of where entangled photons controlled the performance of music in the original version by 2 people on pipe organs in the Linz Dome with 3,000 people attending. And this actually won a lot of awards and was presented at Expo in Osaka and in Washington, DC. Super cool. And then in Vienna, we have 4 institutions. The University of Vienna, oldest university in Austria since 1365, as it says in their claim here. And one of the things that I want to point out here that goes towards gravity and macroscopic superposition is that in Markus Aspelmeyer's group, they managed to trap a bead, a tiny bead, in not at the bottom of a well, but at the top of the well, with super fancy control techniques, actually powered by Technical University of Vienna, or TUV, I think, as we say, right? And in the end, the goal is there to look at the gravitational interaction between tiny masses, which is in fact not known. And then we have TUV, and maybe let me point out here the recent discovery of the possibility to do laser spectroscopy on nuclei, not on atoms. In thorium, in a certain there's a very low energy transition. It's still, I think it's 14 electron volts. So for optics, very high energy, but you can actually, with high harmonic lasers, you can excite excite this transition in the nucleus. And the idea is that it's thought that this transition is so narrow that you could build a clock from it with relative ease, which is basically immune to magnetic fields, electric fields, whatever. And there's a lot of work going on worldwide, and this was really a first there. Thorsten Schumm, fantastic work. And then one highlight from the Academy is the super solids. I don't know if you heard about this. You know about superfluids probably, and you know about solids, but a thing can also be super solid, which is really weird. So it has long range order, but it's also superfluid in a way. So you can have things flowing in there, but the spatial structure of the overall thing is fixed, which sounds totally counterintuitive. And one can prove this by looking at quantized vortices. So this is just one example each. And we have a relatively young institution in Austria. Institute of Science and Technology Austria, which is a little bit north of Vienna. And there, a friend of ours, in fact, yesterday we had quite a bit of discussion about this at UBC, developed an interface to couple superconducting qubits to optical fields, and you can use this as a readout, and eventually also, I think, for essentially getting the state or networking to superconducting quantum computers. But this cluster of excellence has many tasks. It's not just research. It's also supposed to foster training, mostly of graduate students, transfer knowledge into society and technology, and do outreach. And it turns out that we are, in fact, not the physical society, but Cluster of Excellence is the coordinator of the International Year of Quantum Science and Technology in Austria, which has led to a number of activities. And I think the coolest one is a quantum escape game. It's actually a spin-off company of ours that makes games, trading card games, for example, with quantum physicists and quantum questions. And they developed an escape game that they rolled out into 80 schools, developed it in a teacher's education class with teacher sort of professional teacher educators, and did this in 1 week in 80 schools, was televised and on national radio and so on. So, and in just a week from now, we'll have a super cool event in Vienna, Vienna City Hall, with an audience of 1,000 people, just some kind of gala event. All right, and then maybe to finish this up, I talked about spin-offs. My last count was about 9, but I think it's 2 more now. It's probably 11, which is for sure not as many as you have in Canada. And you might have heard that in Europe, we are always a bit slower founding companies. But I have to say that this company, Austrian&Quantum Technology in Innsbruck and Parity QC, they're actually running quite a profit already, right? AQT has been selling quantum computers. They've sold 4 by now, installed, and so they're doing really well. And the rest of it, I think, is not so interesting for you guys here. So this was a very brief wrap up of this cluster of excellence. And for young people here, watch out for announcement for fellowships, PhD positions. There's regular calls. You will find that there is about 70 quantum research groups in Austria, plenty of opportunities. Austria is also a very nice place to live, as Thomas will agree. And if you have any questions about that, just let me know, ask me afterwards. Thank you. And then I'm going to switch to physics, unless you have some specific questions about the cluster of excellence, maybe more in private. Okay, so there we go.
There's this picture.
This is actually, it's going to come. I'm going to explain shortly. All right. So I entitled this Quantum Light Sources, and in fact, I'll focus it, narrow it down a little bit. What I really want to talk about is how and why to get the best and most photons reliably out of your structure. But I want to start with a motivation. Now, I guess one motivation is that we've always been doing foundational experiments. And I had the pleasure to have Thomas work with me on an experiment a long time ago, 1998, where we did a test of Bell's inequality with a sort of novel setup. The idea was to do randomly switched measurements on each site and locally record data. I think this was, in fact, almost the bigger novelty than the switching. It was the local recording and doing correlations in software afterwards. And then one of the things, this is my motivation here, that really made this possible was the source of entangled photon pairs. Okay, and this is super old here, but this source was, so this source, if you detect one photon, comes out in these cones, we detect one here, we'll always find its partner photon there, and if this one's polarized vertically, the other one's polarized horizontally, and vice versa. So this gives entangled photon pairs, and in fact, this picture has almost become an icon for entanglement, although structure itself is not so important. And so then I thought, you know, there's many things that you need in a quantum experiment, and usually it's a source, and then some manipulation, control, and detection, at least with photons. I guess photons are always on their way. They're hard to store. People work on this, but eventually this was what really made this experiment possible and made it much better in terms of you know, the amount of data you could capture in some time compared to previous experiments earlier on. And then immediately, and I think this was Thomas's idea, we turned this into a quantum communication experiment. Your drawing, and made a quantum key distribution system. I'm not gonna explain exactly what this is, but you use the measurement results of these two photons to get random numbers on two sides that are identical, and you will find out if anybody listened into this. It's not a conversation, but into this key distribution. And nowadays, this has become a technology. There's plenty of companies that offer you devices to do this. And again, here you need, and I think you pointed it out yesterday, Thomas, you need lots and lots of photons, right? High clock rates and high quality. This is not the only thing, quantum key distribution, we imagined. This is from a review article by Xiaoyang Liu and Jianwei Pan, if I'm not mistaken, where you could imagine that in a future quantum network, which could be connected by satellites, fibers, various kinds of links, and you might have quantum computers in there, you might have quantum memories, sensors, and somehow you need to bring these together. You know, if you take two quantum computers and just use a regular network cable between them, it's not very smart. If you really want to increase their joint power, you have to connect them coherently. You have to connect them by quantum light. It's the only thing that you can really get to grasp this light. And this brings me to question of what was the picture initially. One of the ways of distributing entanglement or photons beyond what you can do in a fiber, because fiber loss is low, but it's still a number, and if you make the link long enough, you will lose all the light. And one way of avoiding this is to have a satellite that orbits the Earth. And of course, we're all waiting for the Canadian satellite, KeySat. And I don't know, I'm not going to ask about the launch date, but we hope for it. And the Europeans are much behind, you know. Anton Zeilinger's group was actually looking into building a satellite in the early 2000s, but it was impossible, even with this power, to get this going in Europe. And of course, Jianwei Pan in China launched his first satellite in 2016, and the second one is in orbit, possibly more. So we really have to catch up there. And in order to talk to such a satellite, if you live in the mountains like we do, you live in the valley, you need an antenna. You need something to communicate with it, and to communicate with it, you need a telescope. And we actually have a small telescope down here, but there is one problem, and this is this. When the nights are clearest, very often we have fog, cloud cover somewhere in between there. So the idea was go to the top. Turns out the University of Innsbruck has, from the 1920s, a station that was used for cosmic radiation observation. In fact, Victor Frances got the Nobel Prize for the discovery of cosmic radiation, and they lured him to Innsbruck by telling him that they have a cable car. He doesn't need to ride balloons anymore to measure his radiation. And in fact, it was really convenient. It's still very convenient. And so can already see it peek out behind there. We managed to put up an optical ground station using a telescope that is manufactured almost 100% in Austria. And I'll show you a very brief video, which I hope works, of how this was flown up. It's supposed to be sound too, but I don't know if it'll change. Sound's not really important. This weighs 2.7 metric tons, this dome, just this top piece, which was kind of at the limit of what this helicopter could do. This was the short version. If you go on YouTube, you'll find longer versions. It was a very exciting day, and we are super happy that it worked out eventually. And it's now the telescope is already in operation, and to turn this off to avoid the feedback. All right, so this is the motivation. I'm not going to talk about quantum communication today, but this is my motivation for light sources, because even if we go to a satellite, even if it has less attenuation than going through the fiber, we will lose a lot of light. So if you start with very little or with very low rate, you will not get much signal. And so I just want to say a little bit about quantum light sources. Now, your ideal quantum light source should, for example, in contrast to the source I showed you before, deliver you one photon pair or one photon at a time. In this source that we had then, it's really random. And there's a random number of photons coming up. You want these to be in a pure quantum state. That's the state that you need. It should ideally be triggered so that you push a button and out comes this photon, the photon pair. If it's a source of entangled pairs, you also want this entanglement to be maximum. If it's a source that produces one photon after another, if you want to do something with these photons later on, they have to be indistinguishable. We want them to be able to interfere. And if they are different in any way, then they won't. Then, of course, you would like the source to be small. If you put it on a satellite, for example, or if you want to use multiple of these sources, if everyone occupies a whole table, it's not gonna scale. You want to integrate it with other stuff. You want it robust. You don't want a PhD student to be there all night to keep it aligned, and you want it tunable and many other things, perhaps. So, in order to not take too much of your time, I'm not going to talk about all the sources that my group works on. I'm just going to mention two things that might be interesting. You saw this parametric down conversion source before that made the photon pairs. And one way of doing this in an integrated version is so-called Bragg reflection waveguide. Here is an electron microscope picture where now the optical waves propagate in this waveguide, confined laterally by the edge here, and vertically by two Bragg stacks, and this layer composition is chosen such that the long wavelength light. So here you come in with short wavelength light, and this gets converted into a pair of longer wavelength photons at half the energy, twice the wavelength. And trouble is that usually the refractive indices don't match, and so the red wave runs away from the blue wave, and then or the infrared from the red. And so this is inefficient. And with this stack, one can get these just the same, and you can get efficient interaction, and you've confined it to a small volume, and so the interaction is stronger. And here we work with telecom wavelength photons, so the ones that can go propagate through the fiber, and this actually works quite efficiently and can be integrated with lasers. But I'm not going to talk about this. And another work is to make, I talked about purity, to make spectrally ultra pure photons. This is only for the experts, where if you make a pair, you want to make sure that they have perhaps the polarization entanglement, but they have no spectral entanglement at all. So they're completely, if I look at one only, it's completely indistinguishable from the other one. And we just recently made this to be, look at decimal places here. Nice, huh? I couldn't believe it myself, but Tommaso is the first author on this. Is a very, very diligent experimenter. And so this is actually better than Quantum, except that they do it on a chip.
The purity in which regards?
This is single. This is pure spectral purity. So this is the drawing spectral intensity, or actually the square root of it, and it's basically a Gaussian, 2D Gaussian. Quite nice. This is super fresh from October. Yes.
Is it just an accident that you got that purity is?
I think yes. Yes. 0, 0, 0. Yes. We had at least half an hour of a discussion about that. Because there were some of my group who didn't believe it, but it happened to come out that way. And in fact, there is, pardon me? Well, this is actually already, and this is, in fact, this is the error of a mean of a number of separate measurements. And the mean just came out to be that.
If you had measured one more, you could have changed it.
True. Except that every measurement takes, I think, about 10 hours. So, but this is not, these are just two other topics that are going on. What I really want to talk about today are quantum dots. And here we're going to go a bit more into depth. And now quantum dots, I would assume many of you have heard about, but there is a number of different quantum dots. In fact, for this type of quantum dot that is used as a dye or as a marker, which is colloidal, and in fact I think there was a group at UVic that did a lot of work on this type of quantum dots. I just forgot the name of the PI now.
Is that Ruben Gordon or Alex Bro?
Yeah, probably. But it's been so long. And the Nobel Prize was awarded for these quantum dots, for the invention. This is nice and easy to synthesize, but if you want very clean photons, it's very hard. So what we do is we work with this type of quantum dot that is actually grown in molecular beam epitaxy or metal organic vapor physical deposition, and or in this CBE. In fact, some of you might recognize this is from NRC Ottawa. And then there's, of course, another type of quantum dot. And just yesterday, we had a nice visit at UBC where we saw germanium quantum dots. So these are gate-defined quantum dots in a two-dimensional electron gas. But here, usually you don't have any optical interface because there's no, at least in the standard versions. So here you can see these interact with light directly. And for those, I will show you the same thing. Now, what does a typical quantum dot experiment look like? We keep the quantum dots in the cryostat, typically at 4 Kelvin. Why is that? Well, whenever you work in a solid and it's warm, things shake, and that doesn't help to make clean photons. So we keep them cold. They don't need to be super cold, just so that maybe, yeah, that you don't have too many phonons and that the confinement is good. And then you bring in light for excitation. You image to find your dot, and you get the light out, filter it, and measure it. Now, for many years, people have tried to do direct electrical excitation, to put electrodes in there, inject electrons in holes, and get light out. Somehow, it seems that with electrical excitation, you never get clean photons. There have been ideas on how to improve this, but it seems to be very hard. So, and this is why a lot of this talk will center on optical manipulation of the quantum dot state, which avoids creating extra excitations, extra carriers that will create noise and disturbances. And what we then measure in the light that comes out is typically, for example, the lifetime. Look at how the photons that come out of the quantum dot decay away. You might check with an interferometer the coherence of the light that comes out, coherence length. You check what we call the single photon purity, which is a different purity from the one before. So I'll explain this in a second, but it's really just seeing what is the probability for getting 2 photons rather than 1 at from the quantum. And then there's another property, and that is indistinguishability. That is what I said before. If the quantum dot produces 1 photon and the next photon, and we want to do a manipulation with the 2 photons, they have to be identical. And they could be different. They could be different in energy. They could be different in time. They could be different in polarization. They could be different in the spatial mode. And all of these things really have to be the same. If the quantum dot, if anything happens to the quantum dot between emitting the first and the second, they will probably be different a bit. The line might shift around. And all of this you want to avoid. And so if you look into the literature, you will find that many things have been done. People have produced single photons from quantum dots with megahertz rates, several 10 megahertz output. Okay, then they've managed to get 99 point, well, no points here, percent indistinguishability. They've managed to get them very clean. In fact, this is a measurement from Waterloo, I believe, or maybe it was before. My chrono was still in Holland, where now this probability to have 2 photons rather than 1 is less than 10 to the minus 5, which is usually good enough, and in fact, usually limited by the noise of the detector, not the source, because detectors are not perfect either. And then for entanglement, getting polarization entangled photons from the quantum dot, people have also achieved very good values, but it turns out it's actually quite tricky to do this. It is tricky in the sense that you have to take a dot, you have to put manipulators on them to kind of pull on them a little bit to make sure they actually, because they're not round typically, and so the 2 polarizations are not the same, and then you stretch them a little bit and then you make them round, so to say. And so this is not something that you get easily. In fact, also this is not easy, because this has been done, this was done in an open cavity that you have to stabilize, where you have to grow a special structure, and you have to stabilize this cavity inside the cryostat. So many of these things are difficult. For this one, you have to, in fact, have the PhD student realign the source all the time, because the polarization correction is a tricky thing. So how could we improve on that? How could we make a source that's a bit more reliable? And one approach for entanglement was to look into time entanglement, or more specifically, time bin entanglement. And in fact, this is something I was trying to do since Waterloo times. And, you know, every few years we make a step. There's a lot of work in between. And what do I mean by this? So we can encode quantum information, just like in classical information. There's various ways of encoding it. And one way of encoding information is to put it either to put the power or the photon into an early or late time slot. In classical communication, you would call this pulse position encoding. In fact, it exists, but is not used very much. Now, this is easy. So you call this, maybe it's a 0 and this is a 1. And if you have a superposition, a 0 plus 1, then photon is sort of with half probability here and with half probability there. Now, if you want to analyze this, it gets a little trickier. You need to make a superposition of the early and late time slots. So you delay this one, and this one takes a short path, and then here the early and the late meet at the beam splitter, and you can measure the superposition state, the early plus late with a certain phase that you set in the interferometer. Okay, and to do time bin entanglement, you have a source that makes these pairs either in the early time slot or in the late time slot, and then you analyze them again, these interferometers, and this would then be our state, early plus late quantum state. Okay, so then many years ago, a very naive Gregor thought, well, we could do this with a quantum dot. Now, back to some physics. What is a quantum dot? If we look at the band diagram, you have the valence band, the conduction band, holes and electrons, and discrete levels, because now you have a small region, this is the quantum dot, where electrons get trapped and confined and holes get trapped and confined. So now if we bring in laser radiation and promote electrons to the conduction band outside, we take a laser with much more energy than this. And then this band gap here, you create lots of electrons, lots of holes, you wait a little bit, and eventually you create, there's an electron in the hole. Sometimes there's only one, not the other, but that we can distinguish. And if you wait a little longer, there is two of them in there, and then it stops because you can't fit more electrons in here, which is what Wolfgang Pauli told us a long time ago. All right, so now if you wait again, a first pair will recombine and emit one photon. We call this state, we call the bi-exciton, sort of double excitation in a way. Emits one photon, leaving one whole electron pair in here, which if it recombines, emits another photon. So and then I thought, well, what could we just, send in two laser pulses, and then we would either get this pair in the early time slot or the pair in the late time slot. Makes sense, but there's one problem, that if we do it with this laser with the high energy, there is no coherence. This early emission and the late emission happen completely randomly and independently. And this is not entanglement. This is a mixture of having either a photon here or there or both, in fact. So what to do? And then this is almost ancient history, but about 10 years ago or a little more, we figured out that there was a way to do this. So here again, we have our two states, the exciton and the bi-exciton state. And now drawn in an energy diagram, this one electron hole pair, two electron hole pairs, we notice that they don't have the same energy. This exciton has a bit more energy than the bi-exciton state. So now if we bring in a laser that bisects the total energy difference, we can actually, in spectrum, if we now look at the wavelength, we can fit the laser pulse in between these two spectral lines, and simply by spectral filtering, eliminate the laser. Because this is a problem, right? If we shoot at our quantum dot with a laser that has the same energy as the photons that we want to measure, you shoot in, I don't know, trillions of photons, and when I detect one, it's not going to work. It's going to scatter everywhere. And but now what's different is that we directly drive this bi-exciton level, bypassing the exciton, and then when it decays, we get the photon pair, and the laser light doesn't bother us. And it keeps the phase. And we did this, this is in fact quite old, as I said, from, it's a spelling error, from Ottawa, on nanowire quantum dots. And these are very nice, they grow them, this is an actual light from microscope picture. They grow indium phosphide, and then at some point they switch on some arsenic, and it's indium arsenide phosphide, and it gives a trap for the electron and holes. Somewhere in the middle, they grow it longer, and they grow a shell around it so that it's tapered and works as an antenna for the photons that leave the quantum dot. And we did just that with this 2-photon excitation and measure the density matrix with, well, sort of moderate entanglement. One of the problems being that what we don't do here is we don't avoid double excitation. Because if two of these pulses come in, we can get a photon pair in the first slot and in the second slot. So we really have to dim the laser down to give us, on average, just one pair. And this, in fact, is one of the limitations why we don't get good entanglement here. But we didn't know how to do it any better, at least not practically. The theory, of course, already Christoph Simon, you might know, University of Calgary, already had the idea much before 2005, that, well, if you change this scheme and you start from a third level here or a fourth, and then from this M metastable level, you go up there. If it then decays, you're down there and it does not get re-excited a second time. Okay, so in this case, we would only get one photon at a time. And more concretely, if we have this extra level here, we prepare the quantum dot in this, what is a dark state, and then put the pulse in that with 50% probability, or create a 50-50 superposition between the bi-exciton and this dark state or the metastable level. And then you can either have the decay and get a pair or not. And then with the second pulse, you get sort of conditional transfer of population to the bi-exciton level. And here you would actually generate a single photon pair that is either in the early or late time bin. Okay, so this was the idea, but we didn't have the metastable level. We didn't have a way to get to it. I mean, there were some ideas for those, but how do you get there? And on the way to this, we're not quite there. Actually, we have the levels now. We don't have the time bin entanglement yet, but on the way there, we did a lot of work on coherent control of quantum dots. And now, of course, in quantum optics, you always look to the people who work with actual atoms, and they have it easy. Once you trap the atom somewhere, every atom is the same. Same isotope, it's the same everywhere in the universe, or at least in our visible universe. With quantum dots, it's different. They live in a solid, and they scatter things. Every quantum dot is different, and you really have to work on addressing them. And so, and I'm not going to go into the details of that. This is a small selection of possible excitation methods for quantum dots. Okay, various types of lasers that somehow manipulate state. Perhaps the very simplest one, though, is something that you should all know if you've had your basic quantum mechanics. We call it resonance fluorescence. You have a laser that is resonant with the transition of your two-level system. And what happens, of course, is you turn it on, and there will be Rabi oscillations. The atomic population will oscillate between the ground and the excited state, and possibly decay some point spontaneously. And one can do this with quantum dots. The tricky thing being that here, the laser light has exactly the same energy as the photons that come out. So this is the problem that we had before. And I will show you how this is done, but then people manage to observe this, and you see the called Rabi rotations. Just the subtlety here, an oscillation, and if you have so-called pi power, you rotate the Bloch sphere from the ground to the excited state, and if you put more power, you go down again. And people got very nice single photon properties and indistinguishability. This shows the single photon purity again. No peak here in the middle means no probability for two photons at a time. And the fact that there is no peak here, but a peak there means it's also very indistinguishable. I'm not going to explain exactly how these come about, because we don't have that much time. So how does one isolate the laser light from the single photons? You do it by cross-polarizing. You go in with one polarization with the laser light, and the light that comes out, you take the other polarization. Trouble being, you waste half of the photons. So your single photon source is only half as efficient. But that's not the biggest deal. The biggest deal is that you need to suppress by at least 7 orders of magnitude the laser light. And that can only be done by very careful alignment and into the cryostat, or you go through windows, you go through optics. Even the sample itself might create a distortion, and then you have laser light in your output, and the single photon nest is gone. So this is what actually takes a lot of work, and in fact also very good components. So there's one interesting solution for this, for single photon generation, that our friend Doris Reiter, now in Dortmund, came up with, and that is that you take, instead of one laser, you can take two lasers that are on the low energy side of this exciton transition. And it sounds weird. We're taking laser photons that have less energy than the photon that we want to observe, and still we can do a sort of 100% deterministic excitation of the quantum dot. And one way of seeing this is that basically you take that this is a 3-photon process, sort of 2 up, 1 down, and that one actually matches exactly in energy. And this is called super for swing up of quantum emitter population. And on the Bloch sphere, it's kind of describing a spiral to the top here. It doesn't need more power, but it works quite well. And now what is nice, you don't need polarization suppression. You can just spectrally filter this away. And it's also important that it's on the low energy side, because whatever you put into the material on the high energy side will come out with some kind of Stokes radiation, and again poison the output. And here is some measurement data. It's not so great here, but again shows that there is single photons, and also there's well, not so great indistinguishability, but this was more a problem of the sample we had there. Now I'm gonna skip over. Sorry, that was actually. Sorry, no, the wrong slide. I wanted to skip over or something to save some time. And go to another problem that we have with the quantum dots, and that is that even your best grower friend cannot make all the quantum dots the same. Yeah? There's always what we call inhomogeneous broadening or inhomogeneous distribution. So these are aluminum gallium arsenide or gallium arsenide or aluminum gallium arsenide quantum dots, and they have a distribution of wavelengths, say here from 775 to 785 nanometers, or also for the nanowire quantum dots, there's a distribution in energy. The other problem is that even your best laser in the lab will not always have the best day, and sometimes move around in energy. So what do you do? If you want to do the resonance fluorescence that I showed before, you have to be exactly on resonance, to be exactly matching. If it moves away, it doesn't work anymore. So how to solve this? And there's a solution again from atomic optics, and it's called adiabatic passage or adiabatic rapid passage, where you remember the Rabi oscillation, you are exactly on resonance, and the population oscillates between 0 and 1 in the upper state. If you detune, if you change the energy of the laser, you will get weaker oscillations, right? Now it turns out, if you do small oscillations, but then change this detuning, you can actually make the population kind of walk up to the excited state. The Bloch vector on the sphere follows the laser field adiabatically, and this is better explained in the dressed state picture, which I don't really have time to explain. But essentially, you have a time varying Hamiltonian. You have a laser field whose frequency changes in time, and this means that the total energy of the system is now not conserved, right? In time varying Hamiltonian, it changes, and this means that the ground state adiabatically evolves into the excited state, and vice versa, which you should have also learned in the quantum mechanics course. And how do you get a laser field that is with time varying frequency? Well, that's in fact also very old. And Donna Strickland received her Nobel Prize for chirp pulse amplification, right? You take a laser pulse, and if that laser pulse has constant phase across all frequencies, then it will also have sort of constant constant frequency in time. And then the laser pulse is as short as can be for a given spectral width by Fourier relation. If, however, I put a phase on this laser pulse that changes non-linearly, quadratically, as a function of wavelength, or in fact, I think the labeling here might be wrong, then I will have a chirp laser pulse. Instantaneous frequency changes. Here, if this is later time, then the high frequencies are late, so it's an up chirp. It's like a chirp of a bird that goes up in frequency. And it could go down. All right, so this is old, but now it turns out if we apply such a field to the quantum dot, and we can do this with the exact same technique as before, the two-photon excitation. Now we have a way of getting from here to there, and it doesn't matter whether the frequency matches. Okay, it can actually vary, and it works on any quantum dot that's within the range. So even multiple quantum dots at the same time. So here we have a pulse that is 0.7 picoseconds long, and we this is just theory for now. Turns out that if you do it on an atom, it doesn't matter whether it's an up chirp or a down chirp. If you do it on a quantum dot, because there's phonons, energy can be lost to the environment. It does matter. Only the up chirp works. How do you make a chirp pulse? Well, you can build this thing here with two gratings. This is exactly how the ultra short guys do it. You have a grating, it disperses. You put a mask in there to change phase and amplitude. You stretch the pulse out. And then with the second grating, you refocus it. Fold this. I think we have 3 or 4 of these in the lab. They're quite a pain. There's a simpler solution, so-called chirp fiber Bragg grating, which you can order from your friends in Jena or buy from a company. And there they inscribe a refractive index variation into the fiber. And this means that one color, say blue color, is reflected here on the left, whereas red goes deeper in and is reflected further back. So this exactly causes the chirp. And now what's really nice is you can use the same fiber from the other side to produce the other type of chirp. And this is very convenient, alignment free, except that the chirp is fixed. So the time variation of your frequencies is fixed, and you need to ask your friend for another batch if you want a different one. And now, if we do this with a little bit of chirp, we still see the oscillation. But if you go further, it just goes to 1. Super convenient.
It will still be power dependent, right? Don't you have to get the optimal power to get this nice transition?
Well, you have to have enough power, because once you're there, it will work for all the quantum dots that are out there.
Sorry, I didn't.
Yeah, no, it's good. And you also see that it doesn't work for the down chirp. It doesn't work very well. You get some excitation, but it's not as good. So you do need more power. That is true. But this is reasonable more power. And one of the nice things, and we already have some results on that, is that you can really talk to multiple quantum dots at the same time. And Dan Balakou in Ottawa, he can grow a stack of quantum dots in his wire. So you can, in fact, parallelize this and could think about sort of multi-user QKD with entangled photons from the quantum dots and other fun stuff. But for us, the main advantage is that you don't need the exact tuning. You don't need to watch it. All right, and I think I've almost exhausted my time. I could still say something about dark states in quantum dots, but it's already almost 3 o'clock.
Yeah.
So I think we should maybe quit here. So let me just summarize a little bit. Basically, this is working on single photons for quantum communication. In fact, the 785 would match very well with Thomas's satellite, one of the projects that we will try to do. And it turns out, in order to use these quantum dots well, you need to you really need to tailor the control of them. And in fact, You've probably heard of people using other types of quantum emitters in two-dimensional materials, TNDs and NV centers and so on. But whatever you do, it's not just the new quantum emitter. You actually need to know how to talk to it. And then a lot of this will improve most of the properties of your photon output. And I want to acknowledge the people who did most of this work. This was the dream team, really. These two guys are gone. The other two are still working. There's some new ones. And here is a group photo. And I want to highlight again the collaborations in Canada here. Other end of Canada, Kimberley Hall at Dalhousie, and then from Phil Poole at NRC Ottawa. And I want to mention one last person who was a mentor for me in Waterloo, where I started this work, and who unfortunately passed away earlier this year at a very young age. But just remember his smile, which was always there and still carries us through. Thank you very much.